This is a lab on orbital motion. And we'll use some NASA data on orbital motion and try to estimate the mass of a distant star from the data that they've posted. So the star is called HR 8799. It's approximately 129 light years away from Earth, which means it takes 129 years for light to get here. So when we look at it, we're actually seeing it as it was 129 years ago. But yeah, they have a published video sequence showing the star and some planets that orbit around it. And, you know, most stars, if not all, actually have planets, which is kind of crazy to think about. So it says try to find the distance to HR 8799 in meters. 1 light year is the distance that light travels in a year. So it's actually like a light year is a unit of distance. So we got to convert our years to seconds. So 365 days in a year, 24 hours in a day, 3,600 seconds in an hour. Okay, if we multiply all of that, let's see what we get. .99 times 10 to the 8th times 129 times 365 times 24 times 3,600. So I'm getting 1.22 times 10 to the 18th meters, which would be 1.22 times 10 to the 15 kilometers. Okay, so quite far. How far is 129 light years? There we go. 1.22 times 10 to the 15 kilometers, pretty far. So it says here, in a two-body system, the rotation of two objects is going to be centered around the center of mass of those objects. So that's one of the reasons that we did those center of mass calculations, you know. There's going to be a distance r1 from one of the bodies to that center of mass, and then a distance r2 to the other of the two. And so why is it talking about, you know, a center of mass between two things? Well, if you go to the sequence, you'll see that there's planets orbiting around this star that we're talking about. Let's go to the sequence. Yeah, the link in the lab will take you to this Wikipedia page for the star in question. It says HR 8799 is a roughly 30 million year old main sequence star located 133 or so light years away from Earth. And it has approximately 1.5 times the sun's mass. And it's part of a system that also contains a debris disk and at least 4 massive planets that we can identify. And so here is the image. It's a moving image here. And you can see at least 4 substantial objects that are moving. Let's zoom in on it. Yeah, okay. Now if you check out the years, like the dates that are posted in the lower left of this sequence, you can see it goes from about 2008, 2009 to 2016. And this was the progress that those had made in that time. Now, I don't know for sure if we're looking at the orbits like totally perpendicularly. I don't know that when we look at these stars, we're not at an angle. And that's something that could throw the data off a little bit. So if the results we get like aren't perfect, that may be a reason why. But anyways, what we want to do is we want to use screenshots from this sequence in order to measure the distance between the planets and the star, or at least approximate them. And we can use the distance and the time to figure out the mass of the star eventually. In the lab itself, there will be 4 particular snapshots taken from the sequence here that you could use to estimate the radius of these from. Let's go back here and explain what this has to do with it. Alright, so there's definitely a center of mass between the star and the planet which is orbiting that star. However, the star is much more massive than the planet. Like many, many times more massive than the planet. So it's reasonable to assume that the center of mass is really close to the star. Likely even inside the star. And so it says here that a center of mass in one dimension would be given by what we had done in the past, which is just multiply the position of the one object times its mass, and the position of the other object times its mass, and then divide by the total mass. Alright, so we're going to come up with an axis where the star is at the origin. Alright, that could be the positive x direction. This can be positive y. Yeah, okay. And so the x that the star is at is an x of 0. And there's going to be an x that our planet is, which I'm calling x2. So this is x1, and that's x2. So if we were to fill in the formula, then we would be multiplying 0, the position of mass 1 times mass 1, plus the distance to mass 2 times its mass. Where R1 would be like the distance from 0 to that center of mass. So this is like R1, this distance here. And then this would be R2, which would have just a little bit different formula. And it'd basically be like R2 equals D minus R1 is basically what I'm doing. So use those formulas to calculate the wobble of the sun caused by the Earth, where the wobble is R1. That would be the distance between the center of the sun and the center of mass. So we'll find out if the center of mass between the sun and Earth is like inside the sun, or is it just outside the sun. Alright, so up above it tells us the mass of the sun and the mass of the Earth. Let's do it over here. So the mass of the sun is 1.99 times 10 to the 30 kilograms, and then the mass of the Earth 5.97 times 10 to the 24 kilograms. R1 would be 0 times the mass of the sun plus the distance Sun to Earth, 1.5 times 10 to the 8th kilometers. Alright, so and then multiply by the mass of Earth. And then divide by M1 plus M2. It's just a center of mass calculation. Could be simplified into this formula if you wish. Let's find out what it is. 8.955 times 10 to the 32 on top. It's basically 1.99 times 10 to the 30 on bottom, because this is insignificant compared to this. Alright, 450 kilometers. Interesting. So, is that inside the sun or outside it? Inside it, right? I mean, we can even look up sun's radius. So, radius of the sun, 432,000 miles. 696,000 kilometers. So yeah, the wobble is inside the sun. All right. So this would be 450 kilometers. And then if we want the radius of Earth, I mean, you're basically doing 1.5 times 10 to the 8th kilometers minus 450 kilometers. So it's a silly question. Like, the significant figures just don't match up. This is totally insignificant compared to that. So R2 is, of course, 1.5 times 10 to the 8th kilometers. So it just shows that the mass of Earth is not that significant when it comes to calculating that center of orbit. You know, the center of mass is actually inside the sun's surface, yeah. Alright, next, what we want to do is we can assume that the sun's wobble is so small that it's negligible according to the calculations. And we can model this situation as if the sun was stationary. So it's like the Earth pulls on the sun in the same way that sun pulls on Earth. And that was part of, previous content. And the idea being that the sun pulls on Earth with a force, which could be called Fg. But Earth pulls back on the sun just as hard. But people don't want to sometimes believe that. It's not intuitive that that would be the case. But it all comes down to what our definition of force and acceleration is. See, Newton said that the forces would be the same, but the object with large mass would not be affected as much. So it's got large mass, so small centripetal acceleration here. So yeah, large mass, small acceleration. Small mass, large acceleration. Alright, anyway, what we want to do is say that that force of gravity is also a centripetal force. And we can use our formulas for both of those things and set them equal to each other and get some interesting results out of it. So the one on the left is, of course, Newton's law of universal gravitation. The one on the right is the centripetal force formula, which says that a centripetal force would be based on the mass of the object feeling the force, the speed of the object, and that would be like a tangential speed, and r would be the distance to the object. So if you set them two equal and do some substitutions here, you can find what's called Kepler's third law for the motion of orbiting objects. Now here we use a quantity which is the angular speed. All right, and we have this relationship that the tangential speed of an object is given by r times omega, where this is a tangential speed, it's called, and this guy here is an angular speed. But we can substitute in that omega equals 2 pi over t, the period. And when we square that and do all those substitutions, we finally find a relationship between the period of a planet's orbit and the distance of that planet to the star that it's revolving around, and then it involves the mass of the star that's exerting the force as well. And yeah, that's Kepler's third law. So you could use that to find, what the theoretical period of these different planets could be according to Kepler's law. We could try one just real quick. Let's try Earth, for example. Let's see, so we have to plug in everything that we know about Earth. We'll have t squared equals 4 pi squared over g times the mass of the star times r cubed. Alright, so there's, Earth's distance of the sun to Earth. We're going to need that. So we'll do 4 pi squared, 6.67 times 10 to the minus 11. That is g. Mass of the sun, 1.99 times 10 to the 30. Distance from Earth to sun, 1.5 times 10 to the 3, 6, 9, 10, 11 meters. Alright, and we gotta cube that. But that, of course, is only gonna give us t squared. So if we want t itself, we better square root all that. 31.7 times 10 to the 6 seconds, which if you convert it, 1 hour, 3,600 seconds, 1 day, 24 hours, 367 days or so. So, okay, close enough. Alright, so that's a Kepler's law calculation there. Now let's try it with this new star. There's going to be a explanation down here, and there's going to be a data table. So what you need is the radius of revolution in astronomical units. That's the distance from Earth to the Sun is a single astronomical unit. So we'll see like how much larger the distance is for these planets versus our planet. And it asks for a measurement in 2010, 2012, and so on. So one option you have is you could print these out and measure it with an actual ruler. Or you could use a computer program, perhaps. So if I say take this image and copy it to a program where I can draw a line, it's just called OpenOffice Draw. So I'll copy my image in. And then all I want to do is just draw a line from the star to one of the planets. Now you may have to look at the, at the lab to figure out which is which, because they have names, these planets. So start with that one. Planet B is this one in the upper left. Alright, so you just want to draw, as best you can, a line from the center of the star to that. Now I may be able to shift it over a little bit. Let's see. Using some of these tools at the bottom. So see, I can kind of manually adjust. All right. And then, see, this program gives me a width and a height. So I got to do my own Pythagorean theorem calculation to figure out how long that line is. Okay, there may be better programs out there for it, which may be faster and easier, but I'll just quickly do that. So I'll do 2.98 squared plus 1.55 squared, and square root that. So we're looking at 3.359 in the units of this program. Alright, but I gotta use the reference that's given here. See, they tell you that this line here is 20 astronomical units. So I'd want to measure that in my program as well. Alright, so that's 1.05 in the program. So yeah, 1.05 for that line. So if I do the calculations, I get 64 AU for that line there. So you'd want to copy that to your data table. Alright, so planet B, the one that I was doing was 2010. Then we don't have to do the plus or minus on each individual measurement. You could just say 64 AU for this time. And then you do it again for 2012. And just see if it's any different. 2012 now. Draw a new line. Okay. 3 by 1.5. So do the calculations. I get 3.34 in the units of this program. Then I go to the reference. That's 1.05 again. So I'm going to take the units of this program and basically just multiply by 20 over 1.05, little conversion there. It tells me 63.9 this time, whereas before it was 64.0. So, okay. Alright, so I'm going to throw another sig fig on there just to be a little more precise. 64.0 AU, and now we got 63.9 AU. So you just keep doing that for each image. And yeah, that'll do it. So it also wants an angle in standard position for each. So for that, I got to use one sample from 2010, and I'll use one sample from 2016. So let me get those real quick, because we want to see how far it advanced in 6 years is the idea. The initial was here. Okay, and according to my program, the triangle that it gave me was 2.98 and 1.55, I believe. Those are just in the units of that program, which are just meaningless, but it helps me find the angle, right? So I can say beta equals the tan inverse of 1.55 over 2.98, 27.48 degrees. Therefore, the theta standard, this would be the initial, 180 minus that, which is 152.5 degrees. But we don't want to leave it like that. We could say 153 plus or minus, maybe up to 5 degrees. All right, that's the initial. That would be an initial angular position, it's called. Now we want a final. 3 by 1.25. Okay, so this is 3 and 1.25. So here our angle will be 22.62. 180 minus that, 157.4. But I'll change it to 157 plus or minus 5 perhaps. And I'll put those results into my data table. So 153, 157. So okay, maybe 5's a little much. You know, maybe I'll lower that to 2. This is the toughest one because it's the farthest one, so it just doesn't advance very far. I don't want my uncertainty to be way too uncertain. We'll try that. plus or minus 2, 157 plus or minus 2. You can get the angular displacement now. Alright, and it, you subtract to get 4 degrees. But then you have to deal with the uncertainty, and they talk about that a little bit up here. Let's see. Better way to get an uncertainty when adding or subtracting measurements would be to use the formula below. So if you have a calculation where you're adding and subtracting, which we are with the angles, then we could do this kind of thing. And so let's see. Use this technique to calculate the uncertainty in your angular displacement. Alright, so we would say delta theta, basically. Delta theta will be square root of 2 degrees squared plus 2 degrees squared, 2.8 degrees. So we may say, round it up to 3 then. And we want our estimated period of revolution now. Okay, so that's a little trickier. Let me get the other values for this so that we can do the standard deviation and all that. Alright, so I would go to a standard deviation calculator and just get the mean and standard deviation of those 4 measurements. Alright, this is going to be a sample. Calculate. Alright, it tells me my standard deviation is 1.0. Okay. The mean is 63.1. Alright, sounds fine. Now we want to get the period of revolution for the planet. That would be t. And so there's a formula here for finding the period. And it is already kind of rearranged for you so that you can plug in your time. And that's going to be 6 years. And here, this is the angular displacement. So if I go to my data table, it would be 4 degrees. Alright, but each of those measurements could have some uncertainty. And it tells you here that, if you use the same techniques that we had used in the past, partial differentiation and all that, you could arrive at this formula, which says the delta t will be the original value of the calculation, like the best estimate, times this, which is the uncertainty in your angular displacement over the angular displacement. We're assuming that the uncertainty in the time is nothing, is the idea. So for my calculation, I would say delta t is going to be 2 pi times 6 years over delta theta, which for me was 4 degrees. And since we're trying to find a period in years, I am going to actually convert it to radians. So I'll go with 2 pi over 360, right in the uncertainty as well, because we want delta t. So I'm going to put the uncertainty in delta theta, which was 3 degrees, over delta theta, which would be 4 degrees. I get 540 years for the period, and then you'd multiply by 3/4, so 0.75 there. So I get 405. All right, so it's a lot of uncertainty. But we would, that's what we would put for that planet. You may get better results out of the other planets. So 540 years, and then just do plus or minus 400, which, that's not the greatest results, but I'm sure you can do better for C, D, and E. Let's see what the actual period for that planet is. All right, they give a lot of information here about the star. Here's its planets. Oh, there we go. There's the period. Look at that. 460 years is what they're saying the accepted value for B is. I said 540 according to my calculations. So that's not too bad.